All right, chapter 14, examples. So the first example we're going to look at in chapter 14 is number 6 from your book, and it says find all maximal ideals and then it gives us 4 different ones that we're going to look at: Z8, Z10, Z12, and then Zn. When finding maximal ideals, the quickest thing for us to do is really going to be to draw out what we've thought of before as our subgroup lattice. Really, we can think of it as our ideal lattice as well. So with Z8, our lattice would look like this. So maximal ideal would be 2. So there's A, and B, Z10. We'd have 2 and 5, and then 0 down here. So maximal would be 2 and 5. Z12, we have 3, and we have 2. Let's see, 6 is below both of those. 4 is below just 2. And then 0 is below both of them. So for maximals, we have those 2. So then what about Zn? Looking at these other 3 that we have, what do we see here? We see that it's primes that divide n. So the maximal ideals of Zn would be Zp, where P is prime and P divides n. All right, number 9. If n is an integer greater than 1, show that the ideal generated by n equals n times z is a prime ideal of z if and only if n is prime. Well, it's an if and only if, so we got to go 2 ways on this. So let's start with if n is a prime and AB is an element of Z. Then by Euclid's lemma in chapter 0, we know n divides A or n divides B, which means that A is an element of NZ or B is an element of NZ. Which would mean that it's a prime ideal. Okay, so that's going the forwards direction, assuming that, actually that's backwards direction, assuming that n is prime. Now let's come up with n having to be prime. So, if n is not prime, we're going to do this by contradiction. If n is not prime, n equals st, where s is less than n, t is less than n, and then st belongs to Zn, but S and T do not, which leads to a contradiction. Thus, N is prime. So, in order to be a prime ideal, N needs to be prime. This might be helpful for you to remember as you're thinking about your tests, because I will be asking you about some prime ideals on your test. All right. How many elements are there in the Gaussian integers over the cyclic ideal generated by 3 plus I? Give reasons for your answer. And for this one, I'm going to reference and have us read through together the solution given by the book. So, we know that 3 plus I times 3 minus I is equal to 10. And we know that 10 plus 3 plus I is equal to 0 plus this 3 plus I. Also, I plus this cyclic subgroup generated by 3 plus I is equal to negative 3 plus 3 plus I, which is equal to 7 plus 3 plus I. Thus, every element is every element of the form A plus BI plus the 3 plus I can be written of the form K plus 3 plus I, where K is an integer. So then how many elements do we have? Well, we would have an infinite number. Number 35. Number 35, we are going to reference those last couple theorems that we had, Theorem 14.3 and Theorem 14.4. And we are coming back to that Z external direct product Z that I said, I believe, last chapter that we would come back and reference at some point. And it says, let I be equal to the set A comma 0, such that A is an integer. Show that I is prime, but it's not maximal. Well, as we look at this, let's look at a factor group, why don't we? This group, we would have A comma B plus I, which is really A comma 0 plus 0 comma B plus I. And since I is defined as it is, this is equal to 0 comma B plus I. Now, this lets us see that there's a mapping that we could make to the integers. So we would map, this goes to B. Okay, now, we know the integers are an integral domain, but the integers are not a field. And I believe we saw that in our table at the end of chapter 12. So Z is an integral domain, but not a field. So then we would employ theorems 14.3 and 14.4, and we would see that by 14.3, since it's an integral domain, so since this is an integral domain, we know that I is prime. Since it's not a field, we know I is not maximal. So we just use theorem 14.3 and 14.4 to finish argument. Alrighty, one more example that we're going to do together as a class. Let A be the ideal of a commutative ring and prove that n of A is equal to n of A. And if you look back, you're going to find this defined in number 46. And this is where we're talking about nil radicals. So if you look back, you'll find in number 46 that n of A is defined to be R elements of R such that R to the n is an element of A for some n. And this n actually depends on the R. It changes for each R, or can change for each R in R. Now, it should be clear from inspection that n of A is a subset of n of A. That's clear, right? So we need to show the other is true. So let's suppose that x is an element of n of A, then x to the n is an n of A for some n. But what this means that, if I can get my English correct, so which means that x to the n raised to, let's use m, is an element of A for some m. So that means that x is in n of A. So what that tells us then is that n of A is a subset of n of A. Now we have the subset going each direction. Therefore, they are equal. Alrighty, that concludes chapter 14. Again, if you have any questions, don't hesitate to email me. Thank you for hanging with me for the rest of the semester, doing this via video. I know. I'm not fully there sometimes doing these videos. I have to stop and think every now and then. And it's just like, you have to stop and think sometimes when you're doing problems. You know, none of us are experts yet. And yeah, I know quite a bit about the field of abstract algebra because I've studied it quite a bit. But sometimes we still have to stop and think about things, which is good to stop and think about it. So thank you for putting up with me all semester long and for just making the best of the semester as we finished it out with remote learning. And you guys rock. You guys are the real heroes this semester for just making this work. So let me know if you have questions.